Hi everyone and welcome to another session of Atoms, in which we will explore the fundamentals of natural language processing, or NLP for short. The outline of the session is as follows. We will start with an introduction, and for the sake of completeness, I will then include a session in which we look at more traditional ways to represent text and to handle text data in the scope of analytical models. And as you can imagine, traditional ways, they have their issues. There were certain challenges that we couldn't really address up until fairly recently. And the second session of the lecture, or the second course session of the lecture, will look into more advanced techniques. We will examine the word embeddings. You will remember that this term, word embedding, has occurred. I've used that before in previous sessions, so now we really want to dive into it and elaborate on what that is and what word embedding means and how these magical type of embeddings can actually be calculated. All right, so let's get started. First of all, we talked about language modeling, but there was only a tiny little piece in the big puzzle of NLP. So maybe for a start, let's revisit some application in which using text data is helpful. And as a matter of fact, we can think of many applications in which this might be the case. And I categorize them here into upstream and downstream applications. Now, that's not my terminology. It's used quite frequently in the field. And a downstream application is one that is maybe closer to the end user. It's different from an upstream application, which is more basic, more fundamental, which is maybe something that we do in order to facilitate richer, subsequent downstream type of systems or downstream type of applications, and something more raw, more basic. And language modeling, the application we have discussed so far, I would consider it a more basic, more fundamental type of application, a more basic way to use text data, and therefore I put it under the label upstream application. It's far away from the eventual application in a business organization, for example. Same with POS tagging. We briefly talked about POS tagging, part of speech. POS tagging is concerned with attaching to every word in a sentence its grammatical role. Like this is a noun, this is a verb, this is an adjective. Or another task that is often encountered in NLP is that of named entity recognition. This means that processing a bunch of text, what are named entities, like in this example here, the price of Apple rose yesterday. Apple, for us, it's obvious that we don't talk about the fruit, but the company, but a computer might not know that. How would a computer, how would a model know that the word Apple in this context is a named entity? It's a company or another type of entity. Well, with regard to downstream applications, many use cases can be considered. Classifying, clustering documents is a quite obvious one. Sentiment analysis also fits in here. Remember, sentiment analysis is a task where, given a piece of text, for example, a review, we want to understand the emotion of the author, whether she is positive about whatever she's writing or whether she's negative about whatever she's writing. Movie reviews, product reviews are common use cases in marketing. And that is a form of text classification. Given a review or a tweet or some other type of text, we want to classify, well, is that actually positive or is that negative? Text classification is an umbrella term where sentiment analysis fits in, but you could also envision other types where you want to classify text and assign it to groups. We also have tasks like machine translation. maybe not so common in an economics context, but it's an important task in NLP. Same with question answering or text generation. Text generation, when you want to build a chatbot, for instance, you need a system that can process some input text and then, well, output a corresponding result. For example, if you phrase a question and submit that to a system or chat box, a customer service chatbot, for instance, the chatbot has to understand this text and then generate an answer to that text. And, well, question answering I put here as a dedicated application. When you talk about question answering in the scope of NLP task, that typically refers to identifying the relevant bits in a text that answers some question. So you feed the system a question, you also feed the system a bunch of text, and then you want the system to identify the pieces in the text that would answer the question or that are relevant to the question. So it's slightly different from text generation. And anyways, these are only a subset of all the tasks that you could envision where text data might be useful. And clearly there are good reasons to think about using text in applications, and thus it's important to analyze how we can make use of text. So the big question for start is how to actually input text into a network, if you use neural networks, or more generally into some analytical model. And for neural networks, you now have a good understanding how they work. You see our language modeling, RNN here, that we've seen many times before. We could also consider a yet more basic type of network, such as a feed-forward type of network, where we have just our input layer or nodes, and then we have a hidden layer, where the nodes are typically fully connected, getting a bit cluttered, and where we then maybe have an output node that generates a forecast. And you know how we train this network by feeding it data points. If we have a table, as we typically have when we face structured data, we have our tabular input data set with a target y, and then we have features x1, x2, x3, x4, right? And then we have some numbers, maybe 0 and 3 and 4.5 and -1, and more numbers of these, and how we then take one data point, so one row of our matrix, one row of our data table, maybe the first row we take, and then the 0 goes into the first input neuron, and the 3 goes into the second, and the 4.5 into the third, and the -1 into the last, and then we feed the data through our neural network. The input data to our neural network is a bunch of numbers. It has to be a bunch of numbers for the type of neural networks that we are used to, and this will not change. So we need this mapping. From when we process text, we need this mapping from words to numbers. And you already know that this is nowadays called word embedding. We embed a word in a vector space. And the traditional perspective to this mapping from words to numbers can be depicted with this NLP pipeline or NLP process. We start from some text data sources, gathering data, maybe web scraping tweets or product review websites, to build up a database of text data. And such database is called the corpus. That's it's a big collection of documents, a bunch of text, nothing but a database, but we call it a corpus. And then we run through a chain of operation. This is here my NLP preprocessing pipeline to prepare the text for subsequent analysis. You see this bag of words element here in my picture. So the NLP processing pipeline delivers us a bag of words, whatever that is. And from this bag of words, we extract features. We obtain a representation of our text, which we then feed into some machine learning algorithm that performs classifications, segmentations, or something else, and eventually delivers some new insight. That's a bit like this famous knowledge discovery in databases process, but for text data. And it's for a reason that the text representation, this bit here, looks like a table, because that is what it is. The idea of this standard perspective here, the idea of text processing or text analysis is that we take our text, somehow project it into a tabular form, to have a tabular form, and with tabular data, we can do whatever we like. We know how to handle tabular data. We have many algorithms at our fingertips, decision trees for classification, we have k-means, we also have neural network, we have logistic regression, we have much other stuff. Many more clustering, we have dbScan, we can rule mine association rules, we can do loads of stuff if we have tabular input data. So the way to approach text processing is to somehow bring the text into a tabular form and then just proceed as we always proceeded in machine learning. So let's have a closer look at this traditional perspective. In fact, I call it a traditional perspective. As you will see, things don't change that much when we look at more modern approaches. These word embedding technologies, they also map, well, input text to some structured tabular type or format. So the picture is still valid. It's just that we might go away from this bag of words approach. But let's look at that in a bit more detail to better understand what it is about. So what is the bag of words, and what are the issues that we have with the bag of words model to represent text? All right. Let's imagine an exemplary use case. Let's imagine we want to analyze the reviews from the IMDB database. They have a famous dataset, the IMDB dataset, where you can, well, just download a bunch of movie reviews and then sharpen your text analytics skills with that data. And the reviews, often they are quite brief, like this one here, Pulp Fiction is the coolest movie ever. Sometimes there are longer. We will use the data in the practical, so you'll get to work with this data. And the idea is that we have one document representing one review. The document is a term that represents an entity in our corpus. A document is something that resembles a row in a data table. As in credit scoring or these marketing applications that I bring in a lot as examples, there we have rows representing customers or borrowers. And, well, a document is a bit like that. It's one entity of analysis. In my example, a document is the subject of analysis. We want to do something with documents. We want to cluster them, or maybe we want to classify them. But the document is our subject, our focus of analysis. And then we need features to represent the document. And in this table that I'm showcasing here, the rows, as I just said, they represent our documents in our database or the corpus. And the columns, the features, are just the superset of words that are used in our vocabulary. Superset means that if you imagine all the reviews ever written on movies in the IMDB, what is the set of words that are used in all these reviews? What are the set of words that are used in all the documents in the corpus? That's the superset, and we call that our vocabulary. It's a joint set of all words. And every word in this set contributes one column to our table. So you see the columns titled here despite and worst and joy and movie, and it would go on with many more columns, one for every word that was ever used in one of these reviews. And then the salt values just represent some quantification of how often a term is used in a document. In this example here, the numbers represent counts. So this one value that we see for despite, that could mean that in review 1, we find one occurrence of the word despite. So for instance, besides needing a little bit of alcohol to enjoy, Pulp Fiction is the coolest movie ever. That is subjective, by the way. Okay, so question number 1, how to design the vocabulary in this setting. Is it really plausible? Is it really sensible to really use all the words in the database that we ever encountered? That is a question that should become relevant very soon. But first of all, just accept this as a way to represent text in a numerical form. We build this document term matrix and somehow quantify how often the terms or the words occur per document. To that end, we need our NLP processing pipeline, out of which I want to highlight a few steps. The first step that we typically perform is tokenization. That means we take a bunch of text, like a sentence, and then split it up into individual items called tokens. And that is often done at the word level. But it doesn't have to be the word level. It's a common choice, it's convenient, but it's not mandatory that we split up our text at the word level. If we focus on the word level and have a language such as English or French, German, Spanish, Italian, whatever, many other languages, the whitespace is a candidate character to use for splitting up the text. And if we do that, we obtain this bag of words that is shown here in the example. Considering the sentence, the lecture ended on time. We split it up at the white spaces and then have 6 tokens at all together. Token 1, the, token 2, lecture, and so forth. And this is our bag of words. And now we can discuss, or we could discuss, well, discussing via video is a bit difficult. Okay, what are the possible pitfalls here with this approach? If we take our text and first of all split it up into individual tokens. And one pitfall, or maybe not pitfall, but one issue we could point out is, so what about word order? Well, that's actually a rhetorical question. What about word order? Well, it's lost. In this sentence, I just split up the token from the first to the last one, but after this tokenization, the tokens appear individually. That's one thing that, well, impedes the value or the effectiveness of the bag of words approach. Another thing is that this splitting at the white space, it does make good sense, but clearly is not perfect. It fails when you have word phrases that just belong together but have no hyphen. Think about, for instance, the term big data. It's spelled like that. So tokenization, done in a standard way, would basically find two tokens, one big, the other data. But as you can imagine, the semantics of these two tokens, when they are together, when they appear together, big data, the semantic is entirely different compared to both tokens, both words appearing in a text, but not next to each other. Big data is, well, it's a subject, it's a concept that carries meaning, whereas the word big and the word data, taken in isolation, do not carry this meaning. Big data is about volume and velocity and variety of data. You know the definition, you know the 3 or 4 or 5 or n v model that defines big data. I hope you know that. And all this concept, all these semantics are lost if you consider the tokens big and data individually. That's a big pitfall here with this very first step in the pipeline. The next step is often to filter out words that you don't deem relevant. Now, of course, relevant, what is relevant? Subjective, depending on context, etc., etc. But if we consider tasks like you want to classify some text, you want to understand what it is about, you have a review, IMDB review, maybe, and you want to classify whether it's positive or negative to learn something about the movies and how people judge a certain movie, like Pulp Fiction, should you know it. And in that case, it's often assumed that stop words or punctuations or even numbers and other types of symbols, they don't matter much. Stop words like the lecture, or this on, that's a preposition on. If you want to understand the meaning of text, well, likely you would not need any of these stop words. And there is a good reason to filter them. If we cut down the number of distinct words because of filtering in our vocabulary, well, you have seen the bag of words model, you have seen this document term matrix before. I was illustrating it. One word, one column in that matrix, cutting out words, filtering stop words, filtering punctuations, means you have less columns. Your matrix is not that big anymore. And you should know how reducing the dimensionality of a problem is typically helpful for analysis. And filtering stop words contributes to reducing the number of words or the number of distinct tokens with which you have to cope. And this step is based on dictionaries. We will do that in the tutorial. It's very easily done. It's just one line of code to write, essentially, and then using some dictionary, all the stop words that are identified as stop words in your dictionary will be removed from your input text, as you see it in my example. That's nice, but again, there are caveats, there are pitfalls, issues we just need to be alert of. And one bit is that these dictionaries, or one complication, if you wish, one obstacle, maybe is that these dictionaries they are language specific. That is not gonna really trouble you if you analyze English text. For English dictionaries, there are tons of dictionaries available. Everything is well developed. Should you be in the case where you analyze or work with another type of language, maybe some more exotic type of language? Well, what is an exotic language? I don't know. I don't want to give an example that might put somebody off, but you get my point. Any tools that we need that are language specific, and dictionaries are one example, they are best developed for English and maybe Chinese for your target language or the one that you need to work with. Maybe there is no really good, strong dictionary available. So that is a complication. Also, words that are typically just stop words, irrelevant for analysis, can also have importance in a text. My favorite example here, and I'm not sure whether you can make sense of that, is the cure. Okay, well, maybe this is really a bit hard to appreciate. I'm not talking about diseases, by the way. I should stress that in these times. Should you not know that that's actually a punk rock band? Is it punk rock? Maybe that's not even punk rock. Anyways, it's a band. Maybe you just Google for that, The Cure. Not really sure what results you'll get if you Google for The Cure these days. Maybe I should have checked that before. My point is that is a named entity. It's a band, The Cure. And if you strip out the stop word and just leave the cure in your text, I would be extremely surprised if any type of model that you might throw on your text would realize that that word cure was referring to this band. To be on the safe side, you might want to Google for Cure and Robert Smith. Whose haircut might become a role model for us in the near future. Okay, so back to the lecture. Stop words might be important to understand the meaning of text. Maybe a more neutral example would be the best. Right? That really strengthens. Best is a strongly positive word, sure, but the best makes it even stronger. So the meaning, if I take out the here, is a little bit different. Stop words can be important. Same with punctuations, hyphens, or apostrophes. Think about the name, O'Donnell. Scottish name, maybe. Or Irish, maybe. We first of all take out the apostrophe, and then we have O and Donnell, and then with tokenization we only keep the O and the other is Donnell. So the name would basically fall apart, and downstream systems could not really make much sense out of that. Filtering stop words is sometimes dangerous. That's what I'm saying. And you have to be alert of these caveats, because the text with which you are working might need some special treatment. Another step in the pipeline is stemming or lemmatization. These two steps are alternative to one another, and they have different advantages and disadvantages. The point in both of them is to reduce the number of distinct tokens or words once more. So ultimately, we want to reduce the dimensionality of our document term matrix. And since every distinct word contributes one column in that matrix, reducing the number of distinct words is a good idea to reduce dimensionality. And this is what both stemming and lemmatization are about. And stemming is the basic, the easy, the quick and dirty approach, if you wish, in that you take a word and then you just chop off the end of it. You reduce a term to its basic element, which is called the stem. And then the question is, well, how aggressively do you do that? How much do you take away? And in my example, you see 3 standard stemmers that are in use: the portal stemmer, the snowball stemmer, and the Lancaster stemmer. Well, take it like that. You will use some sort of software when you work with text, and that software will offer you functionality to do stemming. And then if you call the stemming function, you have to tell that function which type of stemmer you want to use. That's in a nutshell how things work in practice. And you see how these stemmers vary in the degree or in their aggressiveness, with the Lancaster stemmer being the most aggressive one, taking a lot away from the word, reducing it aggressively. Portal is a bit less aggressive, and snowball, well, keeps more of the word. Lancaster stemming would basically deliver the document term matrix with the smallest dimensionality, relatively, but maybe this way of stemming is too aggressive and you lose relevant information. Because all the words generate, but also generation, and also generic, using a Lancaster stemmer, they would all be mapped to the word gen. And generation and generic, that are totally different words. And any downstream system would no longer be able to distinguish between generation and generic and generate, because all these words in the original text, would be mapped to the token gen. That's the downside of cutting down dimensionality a lot. In lemmatization, there we basically determine the dictionary form of a word. We don't just chop off the end, we identify the dictionary form. And in my example here, run, runs, ran, running, the dictionary form is run. And if we use stemming and apply it, we would not obtain the same result. Same with mr and is, the dictionary form is be, but stemming could never identify that. So the best a stemmer could do here is to leave mr and is as they are, without noticing that the concept expressed with using these words is the same, and that they could be mapped to the same token. But a stemmer is not smart enough to do that. Lemmatization can do that, but lemmatization, albeit being superior to stemming, is more costly. Because, well, to come up with a good dictionary, you need to carry out some morphological analysis, and dictionaries, again, are very specific to the language. So the question is whether you can afford lemmatization. If you can, it will typically deliver you better results compared to stemming. And, well, I said here no variance due to stemmer choice. That is true, but you might have choice in the dictionary that you use. And then, of course, there would be some variance, again, based on the dictionaries you employ. So typically you apply one of these two steps. Either you stem or you lemmatize your text. These are only a subset of the standard NLP preparation activities, but they are the most important, or, well, they definitely mark a starting point in your journey through the space of NLP approaches. So these we will also use. You will apply them in the practical. And after carrying out these tasks, you take your text, you tokenize it, you filter stop words, and then you reduce the number of distinct tokens by stemming or lemmatization. You have this bag of words that is left after all these steps. The tokenization gives you the bag of words, then you filter out some words, then you further reduce the number of distinct words through stemming, and then you're left with your bag of words. And then we can revisit our document term matrix that now we understand a little better, I hope, and can critically discuss the underlying assumptions. Well, and the key assumption, I believe, is that to process text, it is enough to look for keywords. This data type here, if you imagine that we have some target variable, I could add it, could I not? So we could add a modeling target to our database, and we could call that sentiment. And then maybe the first review is positive, and maybe, yeah, that makes sense. The first could also be positive, and the third probably is negative, and, well, let's say that one is also positive. You know how to do classification. You could use this data, the augmented data, with the target label, and we would not need the ID. We take out the ID. Instead, we have our target variable. We can easily use some machine learning algorithm, a random forest maybe, to classify the sentiment based on our words, our bag of words. The bag of words, the words, the distinct tokens, they give us the features, and we can use these features to predict the sentiments, or at least we could try to. And again, the numbers in the matrix, they could represent the number of occurrences of a word in a document. That works. Sometimes the cell content is simplified to a 0-1 indicator, where we only distinguish whether a word is used in a document or not, as opposed to really counting the number of occurrences in a document. These are two popular forms. We shall soon see one more. But the big question, if we run classification, if we run random forest on this data, is, are the words, and whether they occur or not, is that really indicative of the sentiment? For sentiment, it's maybe good enough. For sentiment analysis, it's maybe enough to just do some sort of keyword spotting. So the word despite, well, for sentiment analysis, probably that's, well, of secondary importance. And for review with the ID 3, I see that the word worst was used. That's clearly a negative word. So my classifier, seeing this use of a negative word in the corresponding document, in the corresponding review, can learn that whenever the word worst occurs, the review is to be classified as negative. And the case number 4 is a bit more delicate. The word worst is used in review number 4, but so is the word enjoy, which is a positive word. And since my matrix displays term frequencies, how often words are used, and since the term frequency of enjoy exceeds that of worst, my classifier could learn that, okay, there apparently was something negative in the review, but there also must have been something positive in the movie which the writer enjoyed, so I classify it as positive. Just spotting the use of certain trigger words, opinion words, the adjectives here. for example, could be enough to do sentiment analysis. If we want to generate text, which is a much more difficult task, you can probably imagine that this is nowhere near to being sufficient. Just spotting keywords, whether they were used in the text or not. That's absolutely not sufficient to generate text or even to answer questions. That would be pretty much impossible if we base or we build our system on this type of data. Now, that's a more fundamental problem. Even if we don't go that far, thinking about language generation, and even if we consider the much simpler task to predict the sentiment of a review, there is still an issue with this matrix, or with this way to represent the text by looking at the term frequency or the occurrences of keywords. And you can actually see it in my example, at least I'm sketching it, or I'm trying to sketching it. If you look at the column movie, we have this 8 here, large value, also the 6, large value. The word movie, remember my setting, this is meant to resemble a database of IMDB reviews. These are reviews of movies. It's not surprising at all that the word movie is used in many of these reviews, is it? It's a no-brainer if you think about it that the word movie is used a lot. That's going to be a very frequent word. You would see the same in real data with stop words, should you not filter them. Stop words are used a lot. But maybe the stop words, you might have filtered these. A word like movie, in our specific context, IMDB reviews, it's a no-brainer that that word will be used a lot and will show up a lot. Over the whole corpus. But a classifier will have difficulties in learning that if we only presented individual documents, where the feature value for movie will often show some large numbers. So it looks more important, these large numbers, at the level of the document, they look a lot more important than they actually are. And you would need to look at the corpus in its entirety to understand that this word is not really indicative of the sentiment, if we agree that our task is sentiment analysis. Very frequent words might look important in our document term matrix, although they are not indicative of whatever the label is. And this is why the most popular weighting or scoring scheme in the scope of this more traditional document term matrix or bag of words model is the TF-IDF score, where we essentially take our term frequency, our TF matrix, which per document just counts how often a word occurs, but we multiply the TF scores and the TF matrix with the so-called IDF scores, the inverse document frequency, to then obtain a TF-IDF matrix. And the idea of the IDF scores is that you take account of the fact that frequent words often show up in a document simply because they are frequent. And the calculation in a nutshell is that you take the number of documents in the corpus in which a word occurred and divide by the total number of documents in the corpus. And I'm illustrating that here for my little toy corpus of only 4 documents, so I assume that I only have 4 reviews and they together make up my corpus. Then you see how I'm always calculating the IDF scores as 4 over something, The 4 is exactly the number of documents in the corpus, 4 in my example, and more interestingly, the denominator is then the number of occurrences. This 1 here, for instance, the word despite occurs in one document in the entire corpus, which is true. So this is the one document where despite occurs. The word worst, the IDF score is 4/2. Well, the 2, and obviously also that 2 here, comes from the fact that the word worst is used in 2 of our documents. You got the idea. And the only reason why we don't use document frequency but inverse document frequency is to ensure that higher values, well, indicate something that's better. Higher values are better. Higher values are what you want. Higher values are associated with infrequent words, and infrequent words are more interesting. A word like movie, which has low IDF score, relatively, that indicates that movie is not an interesting word because it's so frequent, it's always used. It shows up in every document or in pretty much every document, and therefore the fact that a document uses the word movie does not tell a great deal about this document. If I use a frequent word, that's not indicative of what the document is about. It's the infrequent words that are used in a document that are characteristic. At least this is the premise, or the assumption, if you wish, on which this approach is built. In practice, you typically calculate the TF-IDF score with some normalization. Here's at least a common way to calculate it, where we take the count TF of some token in a document, but you normalize with the total number of words in that document, which does make sense because, again, considering reviews, if you have a review that's very short. Love that movie. Love that movie. Only 3 words. Could be a review. People post such reviews. I'd never understood why, but they do. Then, well, the fact that the word love occurred in that review, it's somehow more relevant compared to a review that is 1,000 words long and also would use the word love. So you should normalize in some way for the length of the document when calculating the TF scores. And that is shown in this version here. And with regard to the IDF scores, they can be very large. Remember, n is the number of documents in your corpus. That can be a big number. Many, many thousands. If you think about reviews or if you have a corpus of tweets, n is typically a very large number. And then the denominator here is the number of documents in which a specific word X actually was used at least once. That can be a much smaller number, especially for words that are rare. And the log transformation is to normalize these scores a little bit. If you think about it, the largest possible ratio that you could have here is an extreme scenario is where there is a word that's used in every document. That could be something like the word the or such an article. You could imagine that an article might be used in every document. So the ratio would be 1 and the log of 1 would be 0. So the TF-IDF score of 0 is an extreme case, thanks to this normalization with the log that indicates that a word is super frequent. And such words often are stop words. That's also shown in this graph here. But on the other hand, a word being used in every document is an extreme case. More likely, words will only show up in some documents, but since n is large, in many documents a word will not be used, maybe because a synonym might be used. And therefore, these IDF weight can grow very large, and then the log smoothes out that magnitude a little bit, but it's still unbounded. So you have a lower bound at 0 here for the score if you calculate them in this way, but you have no upper bound strictly. In practice, you might, but conceptually, theoretically, the TF-IDF score is still unbounded because n over dfx could, in theory, go to infinity, although your corpus is certainly not infinite. And the +1 is just a smoothing parameter here that is added to protect against divisions by 0, right? If there is a word that's never used, you might wonder, if a word is never used, well, why would I consider it? Fair question. It could be, though, that your vocabulary is not based on your corpus, so you don't make the vocabulary consist of words that are used in the corpus. It could be the case that you just use as your vocabulary the entirety of the English language or another language. And then you want to protect against division by 0 errors or issues here, so this is why you have the +1 in the denominator. And there are some alternative ways to calculate TF-IDF. This is the most popular one, I believe, but I invite you to check out, for example, the Wikipedia page, which is clearly sufficient here for some alternative ways to calculate TF-IDF. And you see the tendencies of these scores, how they are alike. So you can interpret these scores. What's often done in EDA step when you work with text data is that you calculate these scores and then examine their distribution, and that could tell you whether you might want to do a bit more filtering or whether you are happy with the distribution. That's typically done. And then the TF-IDF scores are clearly more insightful compared to just looking at the distribution of term frequencies, which suffer from all these issues. All right, let's summarize the back-of-words model and its shortcoming and open problems. We have seen that it does not take account of word order, which is bad because the ordering of words is important, at least in certain contexts. Compare this is interesting to is this interesting, same words. In the back-of-words representation, these two texts, these two documents. It's a bit awkward, I know, to refer to these examples as documents, but in the scope of the document term matrix, what a document is to be defined. It's not necessarily a proper document as we would think of a document. It could be just the type of text that you're analyzing. So it could also be a sentence, for example. This is what I'm trying to say. The weather is a little bit too good for videos. I hope it's better right now. And right, so word order is lost. And just spotting the occurrence of words, you also fail at capturing semantic relationships. Homonyms are a problem. Bank, the word bank can mean different things. The device you sit on or the financial institution, obviously, and you can't really take account of that. Or synonyms, likewise, they are different. Different words are used, but a model could not really detect that these words, in my example here I have phrases, bear with me, carry the same meaning. I'm sorry. And this is especially complicated when there are subtleties involved. Connotations of words. Beth became a big sister to Mary, or a kind of large sister to Mary. Well, if that does not make sense to you, note that one of these two versions has a mean connotation, or negative connotations in a way. Other challenges arise due to the just mathematical characteristics of the document term matrix, given that every word in your vocabulary represents one feature. This matrix is very high dimensional. Many words, vocabularies are built up of many words. Since in a single document only a few words will be used, a few words relative to the size of the vocabulary, therefore the matrix is also very sparse, and the distribution of counts, whether these are TF scores or TF-IDF scores, typically has a very long tail, which can also often impede analysis with some machine learning algorithm. And I'm, presenting you with this example here to indicate or to just showcase the issues of the bag of words model. If you're envisioning a system that is trying to classify text into categories, a system that's trying to build up an index of web pages, for example. You scrape web pages, you look at the bag of words approach, so you map a web page in this document term matrix. Every web page gives you one row in your document term matrix, and you look at the words that are used on the web page, then here in this example, it would be very difficult for a system to identify what the text really is about, whether this is a text, whether this web page in my example is about music or Christianity. Jesus Christ, I absolutely love Madonna. She's ultra adorable and sings just like an angel. For us, it's pretty obvious. Might not be your taste of music, bear with me. I had The Cure before, right? So that was much cooler. Now I can use Madonna as an example. For us as human beings, it's pretty obvious that probably this text is about the artist. But if we imagine a somewhat stupid system that just screens the individual words and which words occur, there are many words in this text that give a high indication of that text being about religion and Christianity. There's Jesus, there's Christ, there's Madonna, angel is there. Singing also is something that fits into the picture, and these are the key words here, right? So, in a nutshell, you can't really make sense of the context and the semantics with this simple model. And there have been approaches to overcome these limitations. One earlier approach, I'm quoting a source here from 2013, which looks not that old, but the approach called LSA, Latent Semantic Analysis, was proposed a lot before. It's just that I draw on this textbook from Bring New on web mining, by the way, for my explanation. This LSA approach was introduced to address the problem of the bag of words model and the document term matrix with capturing synonymity. If two words have the same meaning, in our document term model, or in our bag of words model, in our document term matrix, the two words with the same meaning would be kept apart. Two words, same meaning, outstanding and excellent. We can discuss whether the semantics of outstanding and excellent are really alike, but I hope you agree with me that these words carry a rather similar meaning. It's the type of word you want to use when writing a reference letter, for example, right? But outstanding and excellent you will have these both words in your document term matrix if you proceed in the way I was showing you. So synonyms are a problem, and LSA tries to address this problem. And the approach is built on matrix factorization. So you take the document term matrix and you factorize it. And you see this equation here. You probably are well familiar with the concept of singular value decomposition, which is a popular approach toward matrix factorization. We sort of split up our big document term matrix into two, well, or three smaller matrices, whereby, and in doing so, we introduce something that's often called a concept space. We have new variables which, well, mathematically are the eigenvectors that, the left and the right eigenvectors that enter these matrices U and V, and we have the singular values and the main organelle of our concept matrix here. That's how SVD works. And in a nutshell, this matrix factorization delivers us a reduction of the dimensionality, because if we want to, let's say, classify documents, we could use the document's concept matrix, the dimensionality of which we can control. And we can reduce that so that what's often done is that we don't really use these three matrices as they are, and rather we approximate here the original document term matrix by reducing the dimensionality of our matrices U and V and sigma. And in sigma you have the singular values, you have them ordered from the most important one to the least important one. So reducing the dimensionality and then maybe taking only a bunch of that still gives you a fairly good approximation of your document term matrix, but then you can use the much smaller matrices for downstream applications. If you wanted to document classification, for example, you would take this matrix where the number of latent concepts that describe the documents are a lot less than the original terms in your bag of words model. And that worked pretty well. This approach toward textual data analysis for document classification, that's still, I believe, a popular approach, maybe as a sort of benchmark, but it does work quite well. The idea certainly is very sound mathematically. And powerful algorithms for matrix factorization exist, so that even with large and sparse document term matrices, that's quite feasible. But the point was to address the synonymity problem. And also there is a very popular approach from this gentleman here, David Bly and co-workers. David Bly, who's now with Columbia, who wrote this 2003 paper in the Journal of Machine Learning Research, which was cited, I don't know how many thousands of times, so it made him very famous. And he used Bayesian statistics to come up with an approach, an unsupervised method to extract latent topics from documents. Roughly speaking, his approach tells you something, what a document is about. So it's a way of clustering documents, if you wish, or classifying. It's a bit, I said unsupervised, so I should say clustering. The idea is as follow. Well, maybe I describe the idea and then you decide whether this is more clustering or more classification. The idea is as follow. You assume you observe a document with the words in that document. That is all what you observe. But you assume, a bit like in the LSA case, that there are latent topics. There is a set of latent topics whereby a topic is just a distribution, a discrete distribution over words. So imagine a topic, data science. The topic is a distribution over words. So words like data and algorithm and probability, they would have high probability in a latent topic, data science. Whereas the same words would have very low, close to zero probability in a different latent topic, cooking. Probability might have some, the word probability might have some probability to show up in a topic cooking, because with some probability, whatever you cook might go bad. But I hope you got the point. So a topic, according to Bly and co-workers, is just a distribution over words. And a document, words from a fixed vocabulary, and a document is a distribution over topics. So multiple topics exist in a document. That's what this picture is meant to resemble. You see the color coding of certain words in that piece of text. It's written in German. If you don't speak German, well, it's not important to understand this text. Obviously, it's text, and some words are color-coded. And the idea is that LDA, that's how the algorithm is called, latent derestrict allocation, would try to disentangle which word in a document are associated or came, in fact, it's a generative model, which topic generated the words that we observe in the document. And some words have been generated, or we assume that some words in this document have been generated from the blue topic. And other words have been generated from the green topic. And then there is a word which we estimate to come from the orange topic. That's the idea. And using then Bayesian inference, we estimate from a corpus, from a bunch of documents, all the latent variables in these models, which are at the document level, the distribution of topics that we have in this document, and also the distribution of words per topics that are the key deliverables of LDA. What's the word distribution per topic? And for an individual document, how prevalent are different topics in that document? And that's called topic modeling. The difficulty then is after the algorithm has completed its work, you need to interpret these topics. You have a meta parameter, which is the number of topics. You say, well, I consider 10 topics. And then ADA, if you run it on your corpus, will basically produce you 10 distribution over words. You get these distributions. And this is also what you see here in the picture. These are the topic distributions, and even if you don't speak German, you will notice that each topic distribution is just a bunch of words ordered by their probability. So what's typically done is you look at the most prevalent words, maybe the top 10, maybe the top 20 per topic, and looking at these words that are strongly associated with the topic, you're trying to make sense of the topic, what it is about. If I'm translating the first topic here, you see the first word is water, the second word is village. So we have water, and we have village, and then we have drinking water, and then we have pond. I should have picked the other one, because the other word distribution is student, university, studies, and one more, students. Anyways, also with the first one, water, village, drinking water, pond. So this website here, which we used for the analysis. That actually was a master thesis which did this LDA analysis here. She was using with a website that offered donors charity projects which they could support. And then we can interpret this green topic as something which has to do with the water supply in the third world, so to say. And the second topic here, the darker green one, there we have prevalent words like student or university or studies. So that is a topic where you could basically support students to financially support students to do their studies. There were charity projects in that area advertised at this website as well. And all I'm trying here is to give you some sense of how LDA is used, not how it works, but how it is used. You get these topic distributions, a distribution over words, in order to process it, in order to have a chance to make sense of it. You cut it down to maybe the top 10 or top 20 words. You look at these words, and then you're trying to make sense. What is this about? And again, here, because you're working with these latent constructs of the document level topic distribution and the corpus level topic distribution, and the topic level word distribution, you can get insight from analyzing your text and then use this insight in downstream applications. So for example, if you want to classify the documents, instead of classifying the documents based on the document term matrix, which is so high dimensional and sparse and has this nasty long tail distribution, you could basically carry out the classification in the topic space that describes the document. You take the distribution of topics in this document and use this topic distribution as the latent feature in your classifier. That is the idea, and that is the similarity also to LSA. There is not only similarity in the acronym LSA, LDA, also how you would use this approach in downstream applications shows some similarity. Okay, so now you have a good understanding of the traditional NLP pipeline and statistical approaches to improve upon the back-of-word model in the form of LSA and LDA. The latter are not very important to Adams. I just wanted to mention them briefly. Should have done it more, well, in a more concise way maybe. And now we can move on to our core interest, which are word embeddings, which is basically the neural network type of answer, or the deep learning type of answer to the question how words are to be represented in a vector space. And this is what we will explore in our next lecture, or in our next